All right, Algebra 1, Lesson 33. We're talking about finding the probability of independent and dependent events. Kind of fortunate that one of the last questions that we dealt with from going over our last test was talking about probability. But we're going to add a different facet to it, which is this idea of more than one thing happening and those multiple things that are happening being independent from one another. So events where outcomes of one does not affect the probability of the other are called independent events. That would be like if I flipped a coin and rolled a dice, right? Does the first coin flip affect what comes out on that dice or die? No. The two events don't impact one another. In fact, in all honesty, whenever I flip a coin, if I flip it again, does what I got the first time affect what happens the next time? No. It doesn't affect it. It doesn't change it. Now, in an event where, let's say I had a deck of cards, right? How many cards are there in a deck? 52 cards in a deck. If I come over to Jeremy and I have Jeremy pick a card, right? And I come over to Mia after that, does what he got affect what she can get? Yes, right? Because whatever he has is no longer in the deck, right? So there's no way for her to get the card that he has in his hand, unless I've got some screwy deck. Okay, so that's what we're talking about when we talk about dependent events. But independent events would be if I had Jeremy pick a card, look at it, put it back in the deck, right? Shuffled it, came over to Mia, said, now you pick a card. Her probability of getting Jeremy's card is the same as the probability of Jeremy getting Jeremy's card, right? Because he put it back in the deck. She can pick any card out of the deck from anywhere. So those are independent events. Do we understand how that works? Okay. So spinning a spinner and flipping a coin are independent events. One does not affect the other. The results of one doesn't affect the result of the other. So what is the probability of spinning a 3 on a spinner that has 5 sectors and flipping a coin and landing on heads? Okay. Well, so we would call this, what is the probability of 3 and heads? So probability of 3 times the probability of heads. So when we have multiple probabilities and we want to know what is the probability of both of these things happening, we multiply the probabilities. And probability is shown as a fraction, right, or a ratio, right, where we have number of likely over number total. So the probability of getting a 3 on a spinner that has 5 equal segments is 1 out of 5, right? Provided that only one of those segments is a 3. All right, so that's why we see this fraction 1 over 5. The probability of flipping a head and getting a head on a coin flip, so long as it's not a 2-headed coin, is 1 out of 2, right? Right? I have one of them that is heads, and there's 2 sides to the coin, right? So do we understand how we get 1/5 times 1/2? All right, well, 1 times 1 is 1, 5 times 2 is 10. So the probability of taking a spinner and spinning it and landing on 3 and then flipping a coin and getting heads is 1 in 10. Okay? And then we could take, 1 divided by 10 and get that as a decimal or a percent. So if we do 1 divided by 10, right, I have a 10% chance, right? Do we understand independent and dependent? Okay, so far. All right. So spinning the spinner twice also creates 2 independent events. The first spin does not affect the second spin. What's the probability of spinning a 5 and then spinning a 1 with the same spinner? Okay, well, the probability of spinning a 5 is 1 in 5. The probability of spinning a 1 is 1 in 5. So I get 1 times 5 times 1 times 5. 1 divided by 5 times 1 divided by 5. 1 times 1 is 1. 5 times 5 is 25, right? So what we wind up with is a 4% chance of that actually happening. Okay? You see how the more involved it gets, suddenly, like, the chances of certain things happening gets really, 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 really small. This plays an effect in games of chance, right? Things like playing the lottery. All right, when you start to add digits necessary to get, the prize, the chances of getting it declines exponentially. Okay? So that's why you hear things like the chances of winning the lottery is the same probability as getting struck by lightning. In fact, you have a better chance of getting struck by lightning than you do winning the lottery just by the mere probability of it. Does that make sense? So don't play the lottery. It's a waste of money. But cool if you win. And, if you want to share that, I feel like as somebody who taught you math and probability, I feel like even just a small cut of it would be appropriate. All right, with dependent events, so these are things that affect one another. The outcome of one event does affect the probability of the other event, like the deck of cards, whether or not we put the card back. To find the probability of two dependent events, you multiply the probability of the first event by the probability of the second event, given the results of the first event. So if he pulls out one card, right, he had a 1 in 52 chance, right? But she only has a 1 in 51 chance, right, of getting any certain card. Now, if we said, what's the probability of Jeremy getting a heart and Mia getting a heart, right? That changes a little bit too, because there was 4 hearts let's see, how many hearts was there? 13 hearts when he started, so he had a 13 in 52 chance of drawing a heart. She only has a 12 in 51. Does that make sense? Because if he got a heart, one less heart, and he kept the card, which means there's one less in the deck. All right, do you see how those things affect each other? All right, so we have different types of events. So this is just independent versus dependent events. So we need an independent event. The definition is the outcome of the first event doesn't affect the second event. So probability of A and B happening is just probability of A times probability of B. Dependent events, the outcome of the first event does affect the second event, changes things, right? If he puts his heart back and she pulls a heart, it's a 13 in 52 times a 13 in 52, okay? All right, odds. You might hear, what are the odds, right? What are the odds of that happening? Or may the odds be ever in your favor, something to that effect. And we might begin to think that odds and probability are the same thing but different words. They're not. They're different things. Okay, probability. Remember what the definition of probability is. What is on top? Number of, you almost got it. Number of desired. What I'm actually wanting, right? So like I said, if I want Jeremy to draw a heart out of a deck of cards, it's 13, right? Because there's 13 of those hearts. Right, over the what goes on the bottom? Total, how many is there? Okay, so odds are different. Odds are number of desired over undesired. Okay, so let's talk about a deck of cards for a second. Let's say that we want those hearts. Well, the number of desired is still 13, but the undesired are all the cards in the deck that are not hearts. Right, so what's 52 minus 13? 39, so it's 13 to 39, right? And we could reduce that though, right? Right? It should be what, 1 to 3? Yeah, it's 1 to 3, right? Okay. And we show odds more often like this, okay? 1, 2, 3. Okay, do we understand that? So there's a difference between 13 over 39 versus 13 over 52. This is probability. This is odds. They're not the same. Okay, do we understand the difference? Number of desired over undesired is odds. Number of desired over number total is probability. Okay? So odds of an event, a ratio of expressing the likelihood of an event. Assume that all outcomes are equally likely and that there are m favorable and n unfavorable outcomes. The odds of the event are m favorable over n unfavorable. The odds against the event then would be n over m. Okay, because I want to know the unfavorable becomes the favorable in a sense. Let's see if I can seem to have lost my little cursor guy here. There he is. All right, so that's it as far as that goes. Let's take a look at Some questions. Okay. They love dealing with these bags of marbles. It's like a really common thing. A bag contains 5 red marbles, 3 blue marbles. What's the probability of drawing a red marble, keeping it, and then drawing a red marble? All right, so we have 2 events taking place, right? So we want to first find the probability of drawing a red marble. What's the probability of, what number goes on top? 5 over 8. Good. 5 over 8. Do we understand where the 8 comes from? There's 8 total marbles. Where are we going to multiply that by? Notice that we're keeping it, right? We're going to keep that red marble. So, and now I want to draw a blue marble. 3 over 7. Why 7? Because I took a marble out of the bag and I kept it, right? But keeping it, oh, and then drawing another red marble. Okay, you're right. But this is what we get if we were trying to draw a blue marble. All right, but let's change this. All right, we want to draw another red marble. So how many red marbles are there to get? 4. So we have 5 eighths times 4 sevenths. Okay, 5 times 4 is 20. 20 over 56. Did I get something wrong here? Did we keep it? Keeping it. I should get 20 over 56. That seems like a wrong answer. Unless we can reduce it, and I'm sure that we can. So what would we get? What, 10 over 23? 514. So yeah, we weren't wrong. We just hadn't reduced it. And we do want to reduce it. Okay? We're good there so far? Okay, hopefully I haven't confused you more than you needed to be. All right, let's take a look at another one. All right, what's the probability of spinning black or spinning a number greater than 3? Okay. All right. What's the probability of spinning black? Notice we have 1, 2, 3 whites. The rest of them are considered black. Okay, what's the probability of spinning black? 5 over 8. Okay. What's the probability of spinning a number greater than 3? Can that include 3? No. So I have to look at 4, 5, 6, 7, and 8, right? How many of those are there? 1, 2, 3, 4, 5. Out of how many? 8. So notice that it says or. It didn't say and. If it had said and, we would have had to have multiplied those 2 things, right? So what we should get here is 5 eighths. I do want to check my answer key, make sure I haven't told you anything wrong here. Number 2. 2 is A. Maybe I was wrong here. Nope, it says 2 is A. Okay, well they're saying that. Let's take a look and see why. All right, we said 5 eighths. One, 2, 3, 4, 5. We had 5 eighths there, 5 eighths there. My guess is that our situation is with the word or. I'm going to take a look at our book. Okay, lesson 33. And see if we can find an example. I'm trying to figure out why they're getting 7 eighths instead of 5 eighths. What's that? So what might be the possibility was the probability of spinning black or spinning a number greater than 3. Let me hit pause on this for a second because I want us to understand what you're saying. I believe it should say and there. What's the probability of spinning black, right? The probability of spinning black is still 5 eighths though, right? Okay, so you're getting 5 eighths and the probability of spinning a number greater than 3. So that's still 1, 2, 3, 4. That's still 5 eighths though. You know, if it has to be both of those things, and it doesn't say and, but if it had to be both of those things, then we would have to get 4 is black and greater than 3, right? 6 is black and greater than 3. 7 is black is greater than 3. 8 is not black, right? So we would be left with, what, 3/8, which again is an option, but it's not the right option. So it is, unless the answer key is wrong, but I kind of doubt that it's wrong. I'm trying to think if there's not just a better explanation on where they're getting that from, and I'll try to come up with it if I can find it. Let's move on. Go ahead.
A through H or whatever, it all has and.
Yeah, so I don't think that you're going to run into one of these ors anyway. Yeah, I mean, yeah, I don't think that we're going to have a problem there. If we do, I'll try to figure it out for you. All right, let's move on. Let's see, what time are you guys out of here? 48, so we got time. All right, determine whether the events are independent or dependent. Each player on the soccer team can choose a jersey from the team jersey set. And each jersey contains a different 2-digit number from 10 to 99. Chris chooses 32, then Pat chooses 77. Are these events independent or dependent? Dependent. Why are they dependent? Right, because Pat is choosing after Chris, Pat doesn't have as many jerseys to choose from, right? He can't choose 32. 32 is no longer an option for him, right? So these are dependent events. All right, let's look at number 4, and hopefully I don't mess this one up. Okay, a bag contains hair ribbons for a spirit rally. The bag contains 3 blue ribbons, 9 green ribbons. Somebody, I'll try to move this over. It's like Malika selects a ribbon at random. Then Jessica selects a ribbon at random from the remaining ribbons. What is the probability that Malika selects a blue ribbon, Jessica selects a green ribbon? All right, so let's talk about the probability of the blue ribbon. What number goes on top? 3. What number goes on bottom? 12. Okay, and then we want green ribbons. Okay. Now for Jessica, what number goes on top? 9. What number goes on bottom? No, because she didn't put her Malika didn't put her ribbon back, so it's 11. So 9 times 3 is what, 27? 27, and then we need 12 times 11. 131, 121, 132. We're getting all kinds of crazy numbers. 132. Okay, we should be able to reduce that. We can probably divide everything there by 3, right? What's 132 divided by 3? 9/44. Okay. Okay. All right. A bumper car ride at the state fair has 3 red cars, 4 green cars, and now 2 blue cars. That adds a little bit more to it. Joe's the first in line on the ride and is assigned a car at random. Bill's next in line, randomly assigned a car. What is the probability that both Joe and Bill will drive a red bumper car? Express your answer as a percent. If necessary, round your answer to the nearest tenth. Okay, so we want red bumper cars, right? We'll get something like that. How many are red? 3. How many total cars do we have? We have 9. Yep, 9. All right, so the next guy up, 2/8. Because there's one less car than there was before, right? So we should get, what, 6/72. We're going to divide that, get a decimal, then multiply it by 100 to get our percent. What is it? Probably a fairly small percent. 6/72 is definitely less than a third, so it's not 33, certainly not 91.7. My guess is either 11.1 or 8.3, and I'm probably going to go with 8.3. Is that right? 8.3%. There's an 8.3% chance that at random they'll both get red cars. Okay? How do we feel about this? Do we feel like we got a pretty good understanding of what's going on at this point? Okay. All right. If there's a question in here that you want to look at before anything else, I mean, there are several questions in here, but let me know and we'll do another one. But otherwise, I'm going to hit stop.